there, everybody. We are getting started with the electricity magnetism unit. So energy unit's done. And so we're going to look at electricity magnetism, and I'm going to do a review of a bunch of stuff that should be familiar from grade 10. But I'll just cover a lot of little stuff that's kind of background information. And then the main skill you're going to be practicing in the assigned work to do with this is about solving circuits, so determining what the current and voltage would be at each spot in a circuit. But in order to have that make any sense, you kind of need to know what the heck current and voltage is and what circuits are and so on, of course, right? So it's just a little bit inconsistent as to what someone's background is from grade 9 science, because that's the last time you would have seen electricity stuff. So yeah. Obviously, static electricity may have been covered. The idea of static charges built up, a bunch of electrons built up somewhere, or a bunch of electrons missing from somewhere, right? So like lightning happens because of a bunch of electrons that are built up and then they repel away and they ground out to the earth and so on. Versus, so this is just charges built up in a spot mainly, and then they move sometimes, of course, when they ground out. But the main observations of attractions, repulsions, and things sticking to things and so on is just because of charges that are built up and staying still. So it's called static electricity. And then current electricity is when electrons are flowing through a circuit and they're delivering energy from a source, like a battery or whatever. Okay, and so yeah, static versus current electricity. And so there's a demonstration I love to do in class where if you sit down on a chair and wiggle back and forth and then stand up and then reach down and touch the metal part of a chair, the classic like plastic chairs with the metal legs in a classroom, you can get a good shock, a good spark that goes back and forth. And the static electricity stuff you hopefully have seen before, where you charge by friction and so on, right? It's based on, I'll go to the video here, chair sit, describe a bit more when I have the video. So let's just do this one for now. So there's a different strength of attraction to electrons between like the fabric of the jeans or the pants material and the plastic chair. And so when there's rubbing and even actually just the separation of standing up, one of them will have a stronger attraction. If one of them has a stronger attraction for electrons, it'll end up with a bunch of extra electrons, and then those electrons will repel away from the built up and negative charge and arc out. And so you'll see little lightning bolt zap there. And so that's charge just built up. So that's just static electricity and charge built up. This is something you can do as well with this. It's surprising, actually. Some people are surprised, at least I was when I first saw it. You can actually get that spark, that jump of electricity go through a light bulb, and it actually makes the light bulb flash, which is kind of cool. I was surprised actually to find that a large fluorescent bulb was even more impressive. It's not even dark in the room and you can see it flashing. So, and it's neat, you can just sit down and, sit down and shop, stand up, shop, and so on. Just the act of coming into contact and then separating separates charge. Obviously, that's not a typical way of lighting light bulbs and so on. So more common ways to get electrons moving and send energy around a circuit are familiar, right? Batteries, solar panels, the plug in your wall, which delivers, energy that's electrical energy that's generated with using generators, giant generators, electric coils. We'll learn about how they work soon. But sometimes they're based on water moving a generator. Sometimes it's coal that's burning, or propane that's burning, or natural gas that's burning, or nuclear energy that we just learned about. Anyways, you're pretty much either using moving water or you're boiling water, right? You make steam and get high pressure. You can move a turbine and so on. So the main concepts in electricity, I do this twice in this lesson, unfortunately, but the main concepts in electricity are electrons flowing, which is current. And just to let you know in advance here, in physics, they historically have talked about the flow of positive charges. Quite literally, they knew about electricity long before they knew about the structure of the atom. And so, they just kind of guessed that positives were flowing, and turns out, of course, the positives are locked tightly in the nucleus and so on, right? So it's really electrons that are flowing, but a ton of learning and effort and work and developments were all sort of written already based on positives flowing. And so it's just kind of carried on with tradition that way. And so we'll refer to current officially as a flow of positive charges, even though we know it's electrons flowing. Although, do we really know? If you watch this video, I'd encourage you to. If you've already done a lot of electricity analysis, you'll hopefully be familiar with the idea of like electrons going through a circuit, delivering energy, and so on. This video by Veritasium shows that electricity is not quite as concrete of a concept as we think. But the main concepts are the flow of charges and the carrying energy through a circuit, right? And so the electrons go around, they pick up energy and deliver it to the load. And then this video sort of delves into some evidence or some ideas about what really happens. But in the end, it doesn't really matter, because this model that we think of works beautifully for what we're doing with electricity. It allows us to predict everything and so on, as you'll see. Okay, so the fact that the energy is actually flowing through the electromagnetic field outside of the wires doesn't actually really matter. It behaves as if it's the way we're talking about it coming up here. Anyway, so yeah, just take a look at that video. It's really good. So I got here. So yeah, electric circuits, obviously a continuous path of a conductor. So something that can allow electrons to move. So we have a battery here. Think of this as a bunch of negatives built up on this end. That's what the chemistry inside of here does. So it separates charges, which are the negatives here, leaving a positive end there. And some of the negatives repel away and they push through here. And as they go through here, they deliver energy. And we'll talk more about that in a bit. But yeah, so the difference in conductors and insulators, obviously conductors allow electricity to flow through, insulators don't. Symbols that are used in a circuit, we'll just see those, these are cells and batteries, lines for the wires and so on, right? So if we're drawing a circuit diagram for this simple circuit here, we just look kind of like that, where we've got a switch and a battery and wires connecting and so on, and there's a complete path for electrons to follow, which is what this red line was. Next here, if you have a series circuit, you obviously draw a series circuit very similar to that. So you'd have a switch. Usually, wires and so on are very curved and bendable and so on. When you're drawing like an electric circuit, I'm really supposed to be using a ruler to do this officially and whatnot, but I'm just trying to make it look somewhat like. So if that's the symbol you chose for a light bulb, I'm doing it kind of backwards there actually. So it goes usually like this kind of thing. Doesn't really matter though. And then looks like the battery was they have the positive, no, they have negatives, yeah. So the small end of the battery symbol is the negative end. It looks like a little negative sign. That's positive end, so you've got negatives repelling out and so on. So this is a more realistic diagram. It's from like a grade 9 or 10, lower grade science book, so they're not confusing or complicating the situation by talking about the theoretical flow of positive charges. But whether positives are going that way or negatives going the other way doesn't really matter. Obviously, at some point, charges are going to be going across the devices and delivering energy, whether they're going one way or the other. Doesn't really matter. So as long as you can make accurate predictions and so on, that's all that science needs to do for us, right? So other ways that this is just literally my previous lessons from previous courses, right? I'm just going to review over in case you haven't seen it. But other ways to produce energy, we have the fuel cells, which sounds like crazy new modern technology, but the first fuel cell was actually invented in 1839, believe it or not. And so this person, Sir William Grove, noticed that water could break down into hydrogen and oxygen by sending electricity through it. And he realized and he noticed that science is quite often reversible. And so he designed an apparatus to be able to show that if you reverse that process, you take hydrogen and oxygen and combine them, you can actually use it to release electricity, which is the exact opposite process. And so that's a gas voltaic battery, which later became named the fuel cell. So forms of electricity. Electricity can be alternating current or direct current. So direct current, electrons are just going around and around all in the same direction. And alternating current, they go back and forth, back and forth. And if you're literally thinking about electrons, picking up energy as they go through here, right? So they pick up energy and then they go through and they deliver energy. It's sort of hard to understand how alternating current can deliver energy because electrons are just going to bounce back and forth. But a nice analogy or a nice model of that, I might have to just pause for a second to find where the video is. It's not here yet. Let me just do a quick pause. All right, I found the link. It's actually in the video I suggested watching above about the misconception with electricity. But to model the main model, like to show a physical version of the main model we have for electricity, it has a chain going through a clear tube, and think of that as the electrons. And so if the chain was flowing, it would be able to turn something if it had an access point. Like there's a little cutaway there, and you can put a wheel there, and it would turn it. Or you could move the chain back and forth, and it would turn the wheel, turn the wheel, turn the wheel. Either way, something moves, right? And so the wheel would just be continuously turning, or it would be whipping back and forth. And either way, you're transferring energy to the wheel. You're spinning it, right? That's the idea of AC and how it could possibly make sense. So the main idea we're talking about, electrons pick up energy, so positive joules, right? Positive work done, and then it carries that energy along, and then it drops it off on here. So when you're measuring the change in the amount of energy that the electrons have, that's actually what we call voltage, right? The change in the potential difference, or the potential, I should say, change in potential, but it's the potential difference across. Change in potential difference is kind of redundant. So that allows us to understand some things, right? In a series circuit, if an electron or group of electrons, actually, we'll talk about that soon, a coulomb of electrons it's called, but just so many electrons moving, you can't really count individual ones. But anyways, a group of electrons pick up 2 joules, and then they go along and they have to drop off energy as they go. And so if these both demand the same amount of energy, then they would drop off 1 joule on each, right? So you can picture the idea of how these work. In a parallel circuit, they have 2 distinct paths. Electrons can go through the bottom path or the top path, and so either way, they're going to have the full amount of energy drop off. That's why loads in parallel get the same amount of voltage, same amount of energy. So these are just simulations that allow us to play with circuits, but it's from a previous course, so I'm just going to skip over that. Drawing circuits we already did. That's just the practice questions through that. I'm just those aren't assigned, of course. The one that's at the top will be the one that you need to hand in. So a nice model for parallel circuits versus series circuits. You look at a parallel circuit modeled like this, and you have 2 completely different paths for water to follow, right? It can go through there and then back up the pump, or it can go this way, and so on. And of course, all of the gravitational potential energy gets given each one, right? So this gravitational energy that's given to those wheels along the way, actually I should have just minus joules, I guess, because it's energy from the system is being taken out, right, and given to the wheels. But anyways, they get the same, each wheel will get the same amount of energy, right? So you could say up here, it's parallel circuits, there's 2 separate paths, and each get the full amount of energy and so on. Whereas in a series circuit, you'd have this where you'd have, I guess 1/3 of the amount of energy. If you had an easy number here, like say 9 joules of energy, then you could say, okay, well, this is -3, -3, -3, for example, or it could be 1/3, 1/3, 1/3. Okay, so there's a single path, and the energy shares. Whereas here we have 2 separate paths, and each get full energy. But the current shares, right? The actual water, some of it goes one way, and some of it goes the other way. So this is like key concepts to understand about how electricity works. Here, each get the same current. All of the water goes through each of those wheels, right? All right, so when we're measuring device, the measuring devices for this, when you're measuring the change in energy, so picture here, there was 9 joules of energy, now there's only 6, and so that'd be a drop of 3. You'd be testing here and here and seeing that there's a change of 3 joules per coulomb. That's what it would read as 3 volts. Okay, so those are measured by voltmeters. That's what in a circuit what you're doing. Okay, so in here, when you go and you put a voltmeter on either side, it's measuring how much energy the electrons have on each side, and the difference is measured as the voltage. Okay, simulation again. When you're measuring current, you have to have current be in line with the flow. When voltmeter, I don't know where the connecting an ammeter is. But when you connect an ammeter has to be connected in series, and so the electrons have to go like through the ammeter along, and it like basically counts them as it goes through. If you were to hook an ammeter up like that, it would destroy the ammeter because they're designed to have no resistance, and so electrons can just go right through. They'll just go in a loop right around like this. It'll short circuit and kill the ammeter if it's not designed to be able to handle the crazy amount of current that would flow, whatever the batteries man is able to push. Current is what is dangerous, and obviously, we see signs about high voltage and whatnot, but the higher the voltage, the more current will flow, of course, in general. But you probably had a chance to play around with like Van de Graaff generators and Tesla coils, and so the Van de Graaff generator like this would make 350,000 volts, but very, very little current, right? So it doesn't kill you. It just zaps through, and you feel the shock and whatnot, but it doesn't hurt you. Electrical resistance, this is just simple stuff, but I mean, like there's different materials that have different amount of resistance than others. The thicker the wire, obviously, the easier it's going to be for electricity to go through. The longer the wire, the harder it is for the electrons to force their way all the way through. And temperature has an effect too. It turns out the lower the temperature, the easier it is for electrons to flow through. So we jump ahead through that stuff. That's just all the things I just said. Clear my throat 1 second. All right, so here we go. As I mentioned, electrons flowing is your current, and then the energy is the voltage. So if we're looking at electric potential energy, you think of like a mass has gravitational potential energy. That's the same way that electrons have electric potential energy. Right? This electron has potential energy because it's going to be pushed away from that negative charge. So you're looking at like thinking of like how electrons carry this electric potential energy. It's very similar to how a brick carries gravitational potential energy as it like falls onto your foot or something. Except, again, the misconception of electricity, it's not quite as cut and dry as we think, but that's a good model for it at least, right? So the equations that go along with these simple concepts, you have the current flow. It's just your number of charges per time that flow, right? That's just a simple flow or rate equation. We have the amount of charges flowing past a point in a certain amount of time. And this is a blurb about how we think of it as the positives flowing, even though that's obviously silly. And then voltage is, like we set up here above, we talked about it's the change in electric potential energy that each coulomb of electrons has, right? So it's change in energy per coulomb of charge. So just simple things like, if it asked how much work is done, well, that's change in energy, right? And so the change in energy would be the variable that you could solve for. You'd have your 18 volts, you'd have your 64 coulombs of charge, and so we're starting to be able to calculate how much energy is carried by a circuit and so on. If we knew this many coulombs of charge flowed or whatever, right? 9-volt battery. So obviously we know that's your voltage. So we have current flowing for a certain amount of time. So current and time, that would allow you to figure out how many coulombs flowed. And then if you know that it's a 9-volt battery, the idea would be, well, each coulomb carries 9 joules, right? Each voltage is literally joules per coulomb right here, right? It's energy per charge. So if there's 9 coulombs going through and each carry 9, think of it as like a wheelbarrow carrying 9 bricks. 9 wheelbarrows go by, you get 9 bricks 9 times. So you end up with this easy concept of 9 times 9, 81 joules. That's what this equation does, right? This equation just represents that logical mathematical equation, or relationship, I should say. Each one's carrying the same amount of energy. If you're worried about, this idea of a coulomb of electrons, just, you look up the conversion factor, right? So a coulomb of electrons is actually 6.24 times 10 to the 18 electrons. It's just a giant group of electrons that was calibrated and chosen as the group of electrons that we think of as a group of electrons that are traveling. Similar to in chemistry, a mole of atoms, for example, is a specific number. Okay. Just makes it easier to count incredibly large numbers if you look at groups of a different large number. So you get like 3 groups or 3 coulombs flowing instead of a bazillion electrons flowed through. So, and like any other conversion, I'd rather you just think of it as the conversion factor, set up the ratio, and just multiply by the appropriate number, right? Second divided by first in this case. So this number divided by that number is what you're multiplying by. Okay. How did we discover some of these things? This is information on this page about the Millikan oil drop experiment. That's how they determined the elementary charge, and then basically calibrated things after that to do with how many charges in a coulomb and so on. So just brief, you should have heard about the Millikan oil drop experiment. YouTube it or whatever, and you'll get some information about how that worked. But they just basically he sprayed little oil droplets between charged plates, and then the oil droplets tended to have like small numbers of additional electrons on them. And so they were able to calculate the charge on a bunch of different droplets and reduce down to, the idea that they're all multiples of a smallest possible number. And so basically we're able to measure that smallest possible charge, which of course is the charge on an electron. So getting close to the circuit solving stuff. And so big thing we need to know is Ohm's law. And it turns out that, of course, the amount of current that flows is proportional to the voltage, right? This is the relationship you see when you do this. And so there's some kind of physical characteristic of a system that is related is the relationship between how much current will flow if you apply a voltage. And of course, the concept is the resistance, right? If you apply a voltage and there's a lot of resistance, not much current flows. If you apply a voltage and there's not very much resistance, then so on, right? So really that proportionality constant is R, and so the slope is R. It's just basically easy development of V equals IR, which is called Ohm's law. And so that's going to be a key equation to use very shortly here. And so there's Ohm's law, your voltage, your current, your resistance. Okay. All right, and then characteristics of circuits. So I already mentioned this previous in the lesson that we know that current is going to be the same everywhere in a series circuit. Voltage shares, so V1 plus V2 plus V3 is going to be like the same as the total voltage. That's that. And then each of the currents are the same. Whereas in a parallel circuit, we've got a path here that this electron goes, an electron that goes through here, drops off all the energy. So these are the same voltages. Whatever voltage this is here is the same as the voltage across here, here, and here. So that's this right here. And then the current obviously divides up. Current's going to go through branch 1, 2, and 3, and then join back up. Okay, so these are just true facts, if you will. I don't know why people say that. Of course, facts should always be true. But yeah, so the total current is the sum of all of those currents through those branches. So the reason I had to show you that, why we should understand it, but also this helps us figure out how resistance, what happens to resistance totals when you add extra resistances in a circuit. Pretty obvious, I think, here that when you add resistance up in series, it's going to get to be more and more resistance. Let's think of an electron having to force its way through here and then force its way through there, and then it makes it harder and harder to go through the circuit. This makes it easier. Say there's a lineup of electrons waiting to go through here. Well, if this one's busy, then maybe they can go to the next one. Maybe there's alternate paths, either like alternate exits from a building. Even if some of them have like a set of stairs, they're a little harder to go through, but there's still a way to go. And so it's going to make it easier to exit a building if there's more exits, right? That's what you think of that as. And so the math works out like this. Okay, so to develop this concept of the resistances just adding up in series, you can think of the fact that the voltages add up And so when you divide through by the current, you get the resistances because V divided by R, V divided I is the resistance based on Ohm's law. That's the easy one. The hard one is to think of the equation that represents, the decreasing amount of resistance each time you add another exit. And how it works is that the current adds up, right? Current in all the branches adds up to the total. And so if we change I's to be V's over R's, and then we notice that the voltages are all the same, you can cancel them all out, you end up with this weird mathematical equation here that accomplishes what we're talking about. So if you put a 2 ohm resistor, a 3 ohm resistor, and a 7 ohm resistor all in parallel, so a 2, a 3, and a 7, right? Each time you add a resistor, the resistance gets a little smaller, a little smaller. Okay, so it's definitely going to be smaller than any of these, the total. So if you add up 0.5, 0.33, and 0.41, and then you solve for the total, it ends up less than the 2. Okay? So you have to recognize here, you can't just flip this and change it to be total resistance equals 2 plus 3 plus 7. Because, math, it's not how numbers work. All right, so this is the one I want to make sure we're good with. It's his review from grade 9, but I mean, that's a little while ago, and you may not have even seen it then. So here we go. We're going to be starting out. Our first task is going to be you're going to be given the voltage and the resistance of each resistance, and you need to figure out what the current is and what the voltage is everywhere, because that's important, right? You need to know how much energy each device is getting and be able to design a circuit to operate properly, right? So determine the current and the voltage everywhere in a circuit. In other words, solve the circuit. So your first step is going to be to determine the total resistance, which in this case is easy, just add them all up, right? Once you have the total resistance, you can use Ohm's law to get the total current that will flow. And then, in this case, once you have the total current flowing, you have current that goes through this resistor. That allows you to solve for the voltage drop. So in series, the total current's the same everywhere. And that V equals IR. And so you're able to solve for voltages across each. I'm doing the idea of it right now, and then we'll do an example. In parallel, what you know is that the voltage is the same across each spot. So if I had a picture of a parallel circuit, the voltage through each branch is going to be the same as the total voltage, right? And so that allows you to solve for the current that goes through each branch. That's the main driving principle behind this. Hopefully this is a review. If not, press pause and slow it down if you need to and watch the video again. But here we go. All right, so we got a nice simple circuit of a 2 ohm and a 3 ohm. So the total resistance, right, is the sum of those because it's just in series. So we get a total resistance of 5 ohms. Then we're going to determine the current that will flow. We have 12 volts applied on effectively a 5 ohm resistance. And so Ohm's law tells us that it's going to be 2.4 amps of current flowing. That's the unit for current, amperage. And so then we know the current through a 3 ohm is 2.4. The Ohm's law tells us that we have this 2.4 amps through 3 ohms. And so V equals IR tells us the voltage drop is going to be 7.2. Once you know that the drop is 7.2 across this one, well, then the rest of the voltage drops on this one. So you can do it that way, where you just be like, okay, well, the total voltage drop has to be 12, so you just solve. Or you can just do Ohm's law again. Okay, so if you just do Ohm's law again directly, you get the balance of the voltage. Sometimes rounding errors will make them not be identical, but that's just literally just that. It's just rounding errors. So some people ask, like, how did this electron know there's going to be more resistance to save energy for? And the answer is pretty simple, where the electrons are going along, they're being pushed against 5 ohms, and 3 of the resistance is here, and the rest of it's here, and so it drops off 3 out of 5 and drops off 2 out of 5. Right? So the total resistance they're pushing against is felt, if you can use that word, but it's the way it works. Okay. Parallel circuit, very similar. You're going to calculate the total resistance, and so that's going to be a 1 over 3 plus 1 over 2 business, right? 1 over 3 plus 1 over 2 gives us 0.33 plus 0.5 and gives us this number, right? So add them up as fractions, right? You can just get them as decimals and add them up, or you want, you can get a common denominator of 6 and end up with 5 over 6, which is the same as 0.833. But just get an answer and invert or like reciprocal or whatever, flip both sides, and you end up with a total resistance of 1.2, right? Less than any of the individual ones, because adding another resistance, say we had the 2 ohm to start out with, the only path to go through is the 2. If we add this extra path in, that makes it easier for electrons to be able to go through the circuit. There's an extra path for them to follow, rather than just having to wait their turn to go through the one path. Now that we have the total resistance, we can calculate the total current. Right? Total voltage of 12 is acting on 1.2 ohms, and so you solve it, you get current of 10 amps. That 10 amps has to split up, right? That means 10 coulombs every second. And so some of them are going to go here, some of them are going to go there. If these were equal, then they'd split up as 5 amps and 5 amps, right? 5 coulombs every second and 5 coulombs every second. But they're not equal here, and so they're going to split up in proportion. But it's easiest just to calculate what the value would be, right? So for the first one, we know the voltage is going to be the full 12 volts, and we know the resistance is 3, and so we just calculate the number, 4 amps. And the other one, same thing, we know the voltage is 12, we got the resistance is 2, so we can divide out and get the current of 6. Okay, so obviously we get, once we had the 4, we could know the balance is the 6, we could do it that way. But either way, it doesn't matter whether you do Ohm's law again or whether you just use the concept of total current. I kind of like to see both, to be honest. It shows full understanding, right? And that's important. Full understanding is a good thing. Okay, so those are the main ones. If you have like a series circuit and a parallel circuit, and then the other thing to watch for is sometimes you have like combination circuits, right? So if you have a combination circuit, like something like, what I have here, I have a picture of it. But I'll show you one here like this, right? It's a combination circuit, and so you need to simplify this thing. You need to like combine those to be a total of 5 ohms, and then combine these to be a total of whatever that is, and then you have the 1 plus the whatever plus the 3 plus the 4. And you get your total, just work on getting your total resistance by combining individual resistances. And so you need to combine everything as much as you can. So any resistances that are in series, add them up. Any resistances that are in parallel, add those up, and so on and so on. Okay, so just combining all the resistances, getting the total resistance overall, then of course you can find the total current, right? Once you have the total current, picture the total current here, you'd be able to get, if you know the total current through here, you can get the voltage dropped. You can get the voltage dropped. You can get the voltage dropped, right? So now you have like out of the 12, maybe 1 volt's there and 2 volts is there and 3 volts is there. Well, then you've got your 1, 3, I got like 6 volts dropped so far or whatever. So then the other 6 is going to drop across here. And that allows you to get the current and so on. Hopefully that makes sense. So what I'm showing here is, add those, get the 5, add those together, get the 0.45. And then you're like, okay, if that's 0.45, oh, by the way, I also did the 1, 4, and the 3 added up to be the 8, right? And so finally we have the 8 and the 0.22 or 2.22, sorry, that ended up being, right? So the 8 and 2.22 adds up to be a grand total of 10.22 amps. So now that you have total current, then you can say, oh, well, I know the total current goes through this 1 ohm and this, and this 4 ohm and this 3 ohm and so on. You can just get the voltage drop across each part. So resistance number 5, for example, it's 3 ohms. There's your total current going through it. 3.151 volts drops there, and so on. And once you have the voltage dropped across each spot, then the remainder drops along here. That's the V parallel stuff, right? You're saying the total voltage is the voltage dropped across the 1st, the 5th, and the 6th. This one, and this one. And then, of course, the rest is in this parallel, dropped across this parallel branch. So you can get the voltage across the parallel branch is 2.64. And then you say, okay, well, I know the voltage across this exact resistor is 2.64 then, so I get the current that flows there. And then you have to realize, like, okay, out of the 1.17 amps, 0.66 is going this way, the rest goes the other way. That's this calculation right there. All right, and so eventually you just end up getting, the current through each spot, and then finally now, since we know the current that's through here, we can get the voltage across each part. Okay, so we have the current through both of them, you get the voltage drop across both of them. There's lots of little sanity checks you can do, or little checks of your work along the way, right? These two voltages better add up to the same as the voltage across that branch, right? That point, what's the voltage across the branch? Where did I do that? 2.64, right? These two numbers here better add to 2.64, which they are really close to, but again, sometimes rounding errors make it so things don't add up perfectly. If you're really worried about it, keep 17 decimal places every time. Yeah, so sometimes you'll have questions where like they don't give you one of the numbers, and so you kind of work backwards and solve, right? So if you know the current and the volt and the resistance it's somewhere, then you can determine you the if you know the volt. I'm trying to think of in this case here, what were we missing? Like we weren't given the resistance there, but we were given the current through here and so on, right? So just basically determine something using Ohm's law, and then determine something else using Ohm's law, and so on and so on. Roughly speaking, anyways, that's the idea. Whew. Okay, so again, that was the main goal was the circuit solving stuff. That's going to be the top page there. Obviously, there's a bunch there to practice. You're going to do a good handful of them and show that you're able to solve circuits. Right? These ones are more concept based, so I'm not going to put them at the top. But you should be able to answer these, like potential difference across the power supply is the same as the potential difference across each of the circuits. Is this true or false? And so on. Or is this either a series or parallel circuit? So if the voltage across the power supply is the same as the potential difference across each of the devices, that must be a parallel circuit, like this type, right? Because that way, if it picks up 10 joules, it's going to drop off 10, drop off 10, drop off 10, depending on which path it goes through. So that is it. Whirlwind review to get us into that electricity stuff. I just need to try and give you some background on where we have come from, where we hope to have come from, and that's it. That's all. All right. Talk to you later. Thanks for watching. Like and subscribe. Share the wealth. All that good stuff. Thanks. Bye.